Well, hello, welcome back. Our next speaker has done a lot of projects in Singapore. He's an environmental engineer, Patrick Bellew. And I suppose when he started his life as an environmental engineer, it was a time when that branch of engineering was really only taught with architecture at the University of Bath. There was still a feeling that architects designed things, and then engineering chappies came along and sort of sorted out the mechanics afterwards, and then the architects got all the credit for everything. How times have changed, and I suppose two particular examples here that I've re-experienced since coming to Singapore for this festival. Firstly, Gardens by the Bay, where Patrick was an integral part of the team led by Wilkins and Eyre, who created those extraordinary domes or biomes and the trees that you see from all over Singapore. And that won the Building of the Year at this festival in 2012. But the jury, interestingly, didn't only want to award the prize to the architects, they wanted to award it to the whole team, which included, of course, Patrick and Neil Thomas from Atelier 1 on structures and Andrew Grant on landscape. I visited the Flower Dome the other day, and it's as cool as ever, literally and metaphorically. It's the first time I'd seen snow in Singapore, or rather white felt placed on little hut roofs in the dome while we were subjected to a lot of Rudolph the Red-Nosed Reindeer Christmas tunes, which rather spoilt the natural image of the flowers. The other project, a smaller project, but I think no less significant actually at the time, I guess must be 20 years old now, which was the Will Alsop reimagination of Clarke Quay, which is now a vibrant, noisy, rather extraordinarily focused place. But the time when Will got the commission, basically it was a quiet bit of a dump, really. And I think it was Capital Land who were the clients, just wanted a complete transformation of the whole thing. And Will did these extraordinary tree structures. Patrick did the environmental engineering. We published this project in Architectural Review. And I must say, I was slightly skeptical about the claims being made that the ambient temperature was lower than the surrounding temperature. But then about a year later, I actually visited Singapore, and I went down to Clarke Quay, saw this amazing thing, stood underneath, and indeed I could feel cool air. And I think it's the only time in my life where I instantly emailed an architect and said, "Congratulations, what you said was true." Now, more recently, Patrick's been involved with a kind of a revamp, a sort of upgrade of Clarke Quay, and a very interesting presentation yesterday by Vector Foil Tech, the manufacturers of the ETFE, which then and now is used for the sort of canopies. And it was a very interesting explanation about how the fritting and the nature of the material they're using has actually taken that project a step further in terms of reduction of temperature, particularly kind of, hot light coming in over the tables where people are eating and drinking whatever it is they're eating and drinking. Well, those projects on their own would have been a reason for inviting Patrick, but as you're going to hear, he's worked on others, I think more recent. So please welcome Patrick Bellew, Atelier 10.
Thank you, Paul. Thank you, Paul. Good morning, everybody. This is very exciting to be here. It's a great honor to be asked to speak at this festival and to see so many friends in the audience. Thanks, Christoph, for the lucky scarf. I've had to put it aside for a moment so I don't boil up, but it's very kind of you. So I'm going to talk about catalyzing the change to a regenerative future as a sort of broad title. And I started Atelier 10 in London in 1990 with working alongside Atelier 1, or structural engineers. And as Paul said, we were working in a world where, honestly, we were still working to a situation where the architects designed the buildings and we put services in to make them work. And we were trying to find a way of having a conversation between architecture and engineering that improved the way that buildings were built. Now, this may seem blindingly obvious now, but back then wasn't so much. We've now grown to be about 350 people in 11 offices around the world, working on lots of projects far and wide. I'm just going to focus on a few of them today. But to talk about, in terms of talking about catalysing change, I sort of start with an anecdote about an Irish client I had working on a project with Foster & Partners. And we had a meeting talking about innovation. And he took me aside after the meeting. He said, Patrick, he says, I want to be innovative. I just want to see where it's been done before. And so you get this thing about innovation and about change that is often, you need to have people who help you to move ideas on. And I'm going to talk a little bit about our sort of journey through gradually embedding sustainability into projects, and then about how we move what's happening now in terms of carbon and what's changing. So actually our first project in Singapore was with Michael Wilford, doing the Durian building, the Esplanade. We worked with Atelier 1 to design the shading system there. I haven't got time to give the full talk on that one, but I'm doing a tour of it later on this afternoon with VM Zinc, if anybody wants to come and see the original hand sketches. The Gardens by Bay I'm going to talk about later. We also were the environmental designers on the Jewel, working with Safdie Architects. And as Paul says, we're still here in Singapore working on things like Clarke Quay and many other projects at Sentosa. So we're very busy in the Singapore market, and it's a wonderful place to talk about regenerative design and about the future of design, because the city is all about that. But as a business, we've had a kind of 35-year focus on operational carbon. Really, what we've all been talking about in this whole time is about operational carbon. And sort of winding the clock right back to the beginning, we did some sort of fairly simple little projects where we're kind of exploring different ways of doing things. This was with Richard McCormack, a little health centre in North London, North East London, where the whole building was actually designed around these sort of ventilation stacks, doctors' surgeries where we could bring, now I've got to find the laser pointer without changing the slide, we could bring air in from a quiet courtyard through an earth duct underground into a little doctor's surgery. He could open a little damper and the air would disappear up a chimney and would naturally ventilate without opening the windows because it was a noisy street outside. So early explorations of natural ventilation. Working with our collaborators of 30 plus years AHMM, figuring out how to do schools as Britain went through a phase of building schools. This was a sustainable primary school where we started to understand that actually with schools you don't want to build heavyweight buildings. You want to build lightweight buildings because schools are only occupied for a relatively short part of the year. They're very rarely occupied in the summer where thermal mass might be a help to you. So what you want is buildings that are pretty responsive, that have great natural light, that naturally ventilate very well. And this is a really iconic little building that I think Paul's in the audience, but will remind me, I think we won about 11 or 12 awards. And the British government being what it is, they never replicated it. It's one of the most successful primary schools ever built, works absolutely beautifully. Still, all made of timber, it's completely sort of sustainable. It's years ahead of its time, and yet never done again because of our procurement system in the UK schools business, madness. We got into thermal mass for university buildings. This is the building with Eva Jurichner and John Tollett at De Montfort University. They were really into natural ventilation, and we said, no, when you've got buildings that are full of students and heat, we should be harvesting that heat through the winter and storing it in the concrete structure. So we developed this system using a system called thermodeck, where we pushed air through the concrete slabs and use that to provide our heating and cooling in a building that needs almost no other systems. I'm not going to go through these in detail. I'm just going to give you a sort of flavor of where we were taken. We started to get into in-ground storage. So this is working with Rick Mather at the Sloane Robinson building. The late Rick Mather was a very frequent collaborator. Geothermal buildings that put energy into the ground. And then a real transformational moment, working with Field & Clegg Bradley. Congratulations on the Kigali win yesterday. We're working with them on that too at the moment. But this was nearly 30 years ago at a place called the Earth Centre. It was going to be UK's Centre for Sustainability, building by Future Systems up in the top, but the building with Field & Clegg Bradley is here. The site sits on a colliery spoil heap, and it straddles two fault lines. So we were the structural engineers for its 30,000 square foot building called the Planet Earth Gallery. We're going to build a giant raft, a huge, deep raft to basically carry this building over the top. I did some sketches which I faxed to Peter Clegg. This is how long ago it was. I remember faxing them to Peter and saying, hey, what about if we hollowed out all the floors underneath and built something that became known as the Labyrinth? Could we find a way of doing sort of the heating and cooling with this sort of underground system? So we developed a graphic to try and explain it. It was one of our first kind of graphics that we produced at Atelier 10. And being a British lottery project, we had no money at all to do it until the day they gave us the money, and then they said, you've got to start on site in 2 weeks. So we had basically looked at the client, looked at us, and we looked at the client and said, is it going to work? And we'd done sort of 2 pages of calculations and thought, yeah, it'll work. So we got on and built it. And so the first labyrinth came out, and this is the innovator part of it, you know, where you're being innovative. This was never really been done on this scale before, probably since the Romans. But it set in motion a kind of a whole series of projects that we worked on down the years. So Federation Square in Melbourne with Lab Architecture Studio. It sits over the rail tracks going into Melbourne Station, and there was a big piazza here, and we had to condition a long atrium space, 350 meters long, that's got an auditorium at one end, but it's completely open at both ends. So putting normal air conditioning in didn't seem like the right thing to do. You didn't want a cooler space that's going to have that. So sitting over the train tracks, we had this space that was between the crash deck and the Civic Plaza. And so underneath, we sort of postulated the idea, could we put a big labyrinth under here that could do our sort of passive cooling? So we did. Another one that got through, the client said, yep, we can, they funded it, and we would have had lots of materials in here anyway to hold the deck up, but we did add quite a lot more. The air travels about 1.2 kilometers down tunnels, and basically the idea is that we take cold air at night, so it's almost always cool in Melbourne in the evenings. Cool air through basically cool down all these banks of cells. So the following day, we pass hot air through, and that hot air chills down before it comes into the space. And the resulting temperature, this is kind of just a quick physics lesson, that this is temperature, and temperature over time is energy. So basically what you're doing is taking the cool from the outside air and storing it in the concrete, and so that gives you the ability to level out the temperature changes. I had the great good fortune to go back there a couple of weeks ago and met Peter and Don, the 2 architects, down in the labyrinth. We had a guided tour of a labyrinth with this very excited guy who manages it, who took on the job of being the head of facilities at Fed Square because he wanted to work on a labyrinth. So a guy, he's called Colin, he's fabulous. And he gave us a fantastic tour through. I would share the videos, but I don't have time, and it's just tunnels. It's miles and miles of tunnels. He said it's a bit like being in charge of a reactor on a nuclear submarine. There's basically nothing to do. You sit and look at it and just hope it doesn't go wrong. But so far it hasn't gone wrong, which is great. But Peter, so 21 years in, climate change has made the temperatures in Melbourne quite a bit higher. But actually, this thing is proving very resilient. It still does a lot of the cooling, all the cooling that we need right through the year. We took the idea to Ankara, its headquarters building with Selçuk Avci, who I studied with at Bath. Ankara is also a country where you get these big variations in day-night temperature. And then in the middle of it's the comfort band, so again, energy into storage. So we persuaded this contractor who were building the building not to do the normal thing in Ankara, which is just to plaster the outside of the building with chilling units, but actually to build a labyrinth in the basement, to do some slab cooling, and to do all the things I was sort of talking about. And they said, it's the Turkish Contractors Association, let's build this thing. And so we built another labyrinth under here. We put slab cooling into the slabs. And the result was, instead of a building which is plastered with refrigerant-based systems, we have PV panels on the roof that run a small blast chiller, and everything else is done with the kind of day-night storage systems. So it's kind of, these things are about trying to shift the way people think about buildings and building design. And we've even done labyrinths at all kinds of strange little structures. The Alpine House at Kew Gardens with Wilkinson Air has a little incy-wincy labyrinth underneath, which you can just see on the top right, the guy's building. Building for United Therapeutics in Maryland, a net zero building we've done with DBB Architects, has underneath it all a large underground energy store, which basically cools the air going into the atriums. Then they open the windows and the air pushes out into the space. So this idea that started as one thing has turned into many other things. We've also started to see the growth of PV, integrating renewable energy into buildings. So this is that particular building with its huge array of PVs to make it overall a net zero building in operation. We've just finished a building with Foster & Partners in Royal Hamilius building in Luxembourg. I've got terrible photos of this, but Darren Haylock from Foster's just sent them through last night, because I said, is it finished yet? And it turns out they have. They've put a big labyrinth underneath this, a whole sub-level, which is all these air passageways you can just about see on this drawing here. And some pictures of the guys from Foster's in the labyrinth testing it out just a few weeks ago as it's commissioned. So it's still rolling. 25 years later, that idea is still running. But I think I just use it as an example of how one can catalyze change. Another project we've recently got photos of is a project by Michel Messessian, the Place Lalla Yadouna in Fez in Morocco. This is in a World Heritage Zone, and we've done a sort of a rework of a big part of the souk in Fez. with some new buildings with courtyards, beautiful ceramic for additional cooling in the courtyards, but again with small labyrinths that sit underneath the buildings so that the air that comes up into the artisanal workspaces is cooled and conditioned before it comes into the space. So all of that just gives you just a sort of an idea of projects, of an idea that's kind of grown and grown and grown and started to become part of our sort of vocabulary, but also is highly intensive in carbon. Building these things takes carbon, and it's something we've become much more aware of as time has gone on. We've tried to do other ways of doing it. So this WWF building with Hopkins in the UK a few years ago uses a slightly different technology where we put, instead of labyrinths underneath, we use concrete pipes in the ground. Oops. So these are called earth ducts. And this is these tubes. And so that uses the the thermal mass of the ground to help us cool the buildings down. And again, we've got this graph that shows the kind of resultant temperature, even on hot days in England, which do happen, 32, 33, we get air off the earth ducts at 15, 16 degrees. So again, free cooling, and it helps us to cool the buildings. And in the States, with Bob Stern, the thing called the Kohler Environmental Center, this was our first net zero building about 7 or 8 years ago. But it kind of shows the scale of the problem. This is a 3,000 square meter liberal arts college building. And in order to make it net zero, these are all the PV panels for the hot water, for the showers, for the resident students. But there's 1 acre of PV in the backyard to make enough power to run the building. So this is part of the challenge, is even when you drive all the loads down, the plug loads you still have in the building, running the power systems, running all those things, still needs a whole lot of energy to make it work, which remains our problem. This building also has earth tubes and all other good things that make the project work here. So you can see a kind of a vocabulary of ideas. And just going back to the Earth Center, back in the early 1990s, or 2000 it was, with Field and Clegg and Atelier 1, designed this beautiful timber structure to support what was at the time Europe's largest 50 kilowatt PV array on a building. And then more recently with Heatherwick Studio and Big, we took the idea of these big domes that they have for Charleston East and Bayview in Mountain View for the new Google headquarters. And these have now become, this is a completely PV roof made of shingles with a sort of 7 megawatt power station effectively on the rooftops of these buildings. So renewable energy is becoming much more a part of the how do we integrate that into the question about how we integrate energy into the buildings. So that's operational carbon. Journey, we understand the components of a journey. We've been on a journey. Operational carbon, driving carbon out is about passive design, active design, plant and kit, and then a bit of renewables, and then you get to somewhere on this point where to get to net zero, you're probably buying green energy, tree planting, other kinds of offsetting. So we kind of get all that now. But with the emphasis on climate change, things have really, really changed. We have to wake up to a pretty big issue that faces us as an industry. The IPCC report says that urgent climate action can secure a livable future for all. But what it does is it projects a series of trajectories, a narrowing window for us to take action to reduce carbon emissions in buildings. And this graph basically shows what happens if in various different scenarios, if we do or how we adopt carbon reductions in buildings. 2030, 2035 is our target date. This is not a long way off. And in terms of buildings, it's about the now carbon that's becoming the big issue. So the embodied carbon is the biggest story in town right now. And we don't often recognize the relationship between embodied and operational carbon in the decision-making processes that we have in building design. So embodied carbon, unless you don't know, is the carbon that's emitted when materials are made, transported, and assembled. So whether that's making cement, making steel, making aluminium, or whatever, you basically produce carbon when you do that. You don't produce carbon when you knock a building down and crush the concrete. It doesn't give off bubbles of carbon dioxide. The carbon dioxide is made by the replacement materials that we put on site, hence the push against demolition. So if you think about the carbon over time in construction, you get these kind of graphs. So with embodied carbon, big amount of carbon up front, that's between now and 2030. Some more as you do fit-outs, maybe a big refit in 25 years or whatever. So you get a profile like that. With the operational, there are multiple possible trajectories depending upon the decisions you make in the process, but effectively it's a longer-term game in terms of embodied carbon. Now what's really changed, particularly in the UK, is our grid, the amount of carbon in the grid, which is what becomes the operational energy in the buildings. Okay? So the grid since 2013 has reduced from about 550 grams of carbon dioxide to less than 200 in 7 years. So we've had this amazing change. So if you use a heat pump to drive building heating and cooling, your carbon emissions are actually very low. Do you know that in a typical London office building, the heating and cooling is less than 15% of the total energy consumption? And yet we focus enormously. So most of the rest of it, I should explain, is plug loads, and it's lifts and elevators and all those sorts of things. That's where most of the energy is going, because the HVAC systems now are so efficient and the coefficient of performance of heat pumps is so good, you don't actually use that much energy to do heating and cooling. And I feel like a complete heretic standing up here and saying this, but that's the reality of this. And so it's the same globally. So we've done some research which just shows the UK is actually running a bit ahead of the curve, but all across the world, all power grids are gradually decarbonising. And that means that the operational carbon in running our buildings is going to get less and less as the years go on. Doesn't mean we should take our foot off the gas, but it means it's going to be less and less. So this is looking at average CO2 emissions globally, around 436. The UK is down at 257. So this does apply to most parts of the world. There are some parts, what I'm about to say, are not so applicable because the grid carbon is still pretty high. So if you look at a building over its life, taking those earlier graphs, the operational and the embodied carbon plotted together, in a traditional old-school building, it might look something like this. So in 5 or 10 years, the operational carbon would overtake the embodied carbon in the building. Now, it almost never does, which means decisions you make, like putting aluminium shades on the outside of a window to reduce solar gain, may never pay back in the carbon terms. I feel like a heretic standing up here and saying it, but we've got to wake up to the fact that sometimes the decisions we make about in trying to save operational carbon have a huge impact on embodied carbon that isn't really recognized in the design process. And we need to understand that better. So in the UK, what we've seen since 2019 is the RIBA Sustainable Outcomes Guide, LETI, has produced a series of ideas and targets, a series of targets and metrics that the industry has fallen in line behind. Our mayor in London has produced guides. The RICS have produced a process that we follow now on all buildings to calculate embodied carbon. So people say, oh, you can't calculate embodied carbon in a building. You really can, and you really can use it as a basis for making design decisions. So in a typical building, we know where the upfront carbon is. We know that there's a lot of it in substructure, superstructure, transport facade, and so on. We're working a lot with Albert and his team at AKT, among many others. We've been working, looking really hard at this operational carbon. This particular project was one we did with Albert's team. And what we start to do, once you know where the carbon is coming from, you can start to make decisions. Do you reduce the basements? Do you move mechanical plant? We build huge basements to put bicycles in London for transport carbon. We've got to start questioning some of those basic fundamental decisions because the carbon impact of that is really high. Challenge, brief, and codes is vital. If I told you that when we first started designing Gardens by the Bay in 2010, the standard roof loading design for Singapore included snow load, because it's a British standard. So it has a 0.5 kilonewton a square meter across the whole roof, which was, when you put it across the roof of Gardens by the Bay, it's thousands of tons of snow on the roof was going to be designed. So we managed to persuade the codes changed to accept a reduced snow loading. But typically we design London office buildings with floor loadings that are designed for a lawyer to have floor-to-ceiling stacked rotary filing shelving, which never happens anymore. It's all digital. You don't need the kind of loadings we put on floors and buildings, and yet every building. So that's real occupancy. That's what we're designing for. Stillage sitting on the floors, or that many people every square meter. So structures are inherently over-designed because of the way that we're briefed. We need to start asking some of these pretty fundamental questions. So basic rule book. What are the things we should try and avoid doing? I love this GIF of demolishing buildings in China, so I couldn't resist. So minimizing demolition is a big part of it. So that on the right there is Space House, a project we're doing. It's a Richard Seifert building we're doing in London just now, which is being refurbished. So minimizing demolition and prioritizing adaptive reuse is clearly forefront. Minimizing basement construction is a big deal. 25% of the carbon in a building is often in basements. We don't even think about it. We just dig big holes and fill it with concrete and steel and all the temporary works that goes with it. So minimizing basement construction is something we need to be talking to our clients about. Structural grids, and again, thanks to AKT for some of this data, if you move from a 12 by 9 to a 9 by 6 grid, you can save something like 20% of the carbon just like that. Now, nobody ever died from walking into a column. You just walk around them. Very straightforward. So, column grids, they don't want columns in the way in office spaces, but you can make office spaces work with smaller grids. Frank Lloyd Wright made it work. It's possible. Architecture can make this happen. Height is a big deal. In Singapore, this is a big story. The taller you go, the more you're resisting sway forces, the more carbon you're going to do to build it. And as the buildings get taller and more slender, the form factor starts to become, the facade carbon starts to take over as a very big driver. The material choices, clearly, whether you're using steel, concrete, and timber, make a big difference, and that also then relates to the grid, so there's lots going on there. Minimizing transfer structures. Singapore loves a good transfer structure. They're kind of incredibly energy intensive. You only have to look at all the materials you see in most buildings in Singapore when they're being built. About 5 floors up in the air, you'll see some huge transfer structure transferring down onto 4 enormous columns. Stop doing that. That uses a huge amount emits a huge amount of carbon. And finally, dare I say it, cantilevers. Cantilevers are, please don't put this in the press. I'll get in such trouble when I get this done. So when you build a big cantilever, it does involve an awful lot of material to basically, whenever you're defying gravity, you're going to be using a lot of material. So these are the things we're learning. These are the toolkit, MEP systems. We put such complicated MEP systems in to minimize carbon emissions in operation and don't recognize the embodied carbon in. So one of the reasons for showing some of the early projects that we did, they were all really simple. We built really simple buildings, really simple systems, and now we make hugely complicated systems to try and reduce operational carbon. We're having to completely rethink that. We have new processes to drive carbon out. So these kind of waterfall diagrams are standard fare on most of our projects now, where you start at a target, and you've got a moonshot goal that you're trying to get to in terms of carbon, and you look at all the opportunities for driving carbon out of the project. This is a new form of process. Some of our clients, British Land in the UK, for example, have their directors' executive bonus scheme is linked to the average embodied carbon of the projects they're building. And the number they have is 500 is their target. They get additional bonus. Nothing focuses the mind of senior executives in projects like a financial incentive geared to embodied carbon in their buildings. These are the sorts of things that we need to start to see changing. We're also seeing the industry change, and we have to recognize the fact that the steel and concrete and aluminium guys are all focused on reducing carbon. In fact, British Steel, just the other day, this was a press release from a couple of days ago, announced they're spending 1.25 billion to decarbonize their steel operations. So we are going to see this changing over time, but we have to put our foot on their throats to keep them focused on this. They're changing because the market is demanding lower carbon steel, and they can't sell their steel into London because London's demanding electric arc furnace steel for all the projects. So everywhere in the world, we need to start putting that pressure on our materials producers to do that sort of thing. So this final diagram in this segment just says the net zero roadmap that we've always developed and understood, which had operational carbon on one trajectory and embodied carbon on another trajectory to get to a kind of thing where we understood the carbon in a building. We have to recognize as designers that there's an enormous interaction between the two fields. It's not two linear processes, they're two interlinked processes, and we have to start using that sort of as a key way, a key design driver in the way that we're thinking about our buildings in the future, because we have to drive the embodied carbon down. And this has been around as an issue for a long time, but we need to fix it. So once we've got there, my talk was supposed to be about regenerative design, but I've rather waffled on about carbon. But once you get to this, what we're just doing, this is a diagram that talks about regenerative design. So what we've been doing for the last 30 years is just trying to figure out how to be less bad. The next question is, how do we start to be better? How do we start to improve and restore living systems? How do we start to be more regenerative towards the environment? And this is where it can get a little soft and fuzzy around the edges. It starts to make us as engineers start talking about a web of life view, about weaving nature's wisdom into the things that we do. This is a different way of thinking about design that's far more focused on nature, ecosystems, biodiversity, holistic impacts. We've been talking about it a long time, but we tend to talk about it in these streams of thought around operational embodied carbon. And we've got to basically get in touch with ourselves and start to ask the question, am I healing or destroying life with these decisions or actions? So that's a big part of what we're starting to try and think of doing. And in reflecting on this talk, I was kind of thinking, Ken Yang has made a career in bioclimatic design. He was quite people didn't take him terribly seriously for a long time. But he's produced some absolutely amazing sort of bioclimatic buildings around the world, and he's kind of a really interesting character in that he was almost the sort of the daddy of bioclimatic buildings. So finally, I just thought I'd tell you a little bit about Gardens by the Bay, because we're here, and it's a great example of, I guess, regenerative, holistic thinking in the way that buildings are designed. So it was an international competition that we entered with Wilkinson Eyre and Grant Associates. Actually, the landscape team was led by Andrew Grant. The gardens are based around the pattern. As you walk around, you might, if you do get a chance to walk around, you'll see that it's actually based around the structure of an orchid. So where the theme gardens are is on the sort of the nodes, which is how an orchid grows. You've got the super tree groves and then the two big glass houses, which were put on that part of a site in terms of master planning to maximize the amount, to minimize the shadow that will be cast by Marina Bay Sands onto that part of the site, because the towers cast quite a big shadow across the site. And we were very concerned about daylight for the plants. So that's the general layout of the gardens with the glass houses to the left. Our big challenge as designers, there was a lot of challenges, but the biggest challenge in the early days was about light. So the plants to thrive need around 45,000 lux for more than 500 hours a year. Now, an office building would be 300 to 500 lux. So 45,000 lux is a huge number in terms of getting light in. We also need to run the glass houses with daytime conditions, which are sort of human comfort levels, but also plant comfort levels for European and tropical montane plants. But at nighttime, we cool the building down to basically give them a day-night cycle. And then what we call vernalize them, so there's an ignition condition where we cool the glass houses down to 13 degrees centigrade for every night for a month, about every 4 or 5 months, which makes the plants think that winter is coming. And so they will produce flowers and actually live in the glass houses, because these are permanent collections of plants. So we need the plants to go through all the motions. So we did so much work around the design of the lighting, working with Atelier 1, working with Matthew Potter, who's here in the audience, with Paul Baker at Wilkinson Eyre, trying to absolutely optimize the structure to maximize the amount of light coming in. And the solution, which is actually a propped grid shell, if you go look at the building, you'll see it's actually a grid shell that's got the steel arch that goes over just stops the grid shell from moving. So it's not actually holding the roof up, the big arch. It's just restraining the movement in the grid shell. And that absolutely minimizes the amount of material so that as the plants look up and see the sky, they see a lot of sky. Now, I should just say that the issue in Singapore is that you only get a 10 to 12 hours of daylight, because it's, as opposed to in Europe, where you get 18 or 19 hours of daylight on a Greek hillside where you're going to put olive trees. And you get clouds and smog for about 40% of the time as well. So the natural daylight's not great. We developed a shading system for the outside, again with Matthew, to help to shade the buildings at certain times. I'm going to zoom through this because there's a book available outside. I'm going to be doing a book signing afterwards, which has the full story in. But we basically integrated in, there's a lot of pipe work integrated into the floor, which basically soaks up the solar energy. The trees and the plants soak up about 60% of the instant energy, turn it into chemical energy, and distribute that through photosynthesis. And then we have an air system that blows air across the floors. The little rectangles you can see on the left-hand drawing here bring air into the space and spread it across the floors. So we only condition space where we need to. And then at the back here, you'll see this big snorkel, which sticks up, and that's the kind of return air shaft that takes air back down to the mechanical room. The big moments on this, and I'm going to zoom through these, go and see the gardens if you're here, if you can. It's amazing. Try and get there when the mountain conservatory has got the foggers going off, because the misting system turns it into this kind of wonderful tropical wonderland. The big breakthrough on the project was when we discovered that the client looks after all of the many millions of trees in Singapore. And we discovered that they give every tree in Singapore gets a haircut once every 2 years. And the guys you see here on the left are part of the teams you see around Singapore who are collecting waste timber. We found out that what they were at that time were doing were taking the waste timber out of Singapore and out of a city rather, and burning it in an incinerator plant. So we intercepted that waste stream. We have about 12 big articulated lorries of wood waste arrive every night into the gardens They go into a chipping plant. They've been chipped, and they go into a big boiler, which generates heat, and one of the super trees has a chimney in it. That heat drives a turbine that makes power. The waste heat from that goes to absorption chillers, and the waste heat from that goes to a desiccant regeneration system that drives the dehumidification and cooling. So the entire garden is run on a kind of circular economy concept from waste products from Singapore. So it's a great story, and it's been a great project to be involved with. So that just shows you some of the kit, which is pretty hard to see, but in the top there is the wood chip that basically runs the whole building. And it's an astonishing project, and one that we thoroughly love doing and have really enjoyed the recognition that's come with it. So I just leave you with this thought. Back to my story about embodied carbon. You know, we know how to do this. We just need to figure out as an industry how to deliver it and how to make it a consistent approach across all the projects that we do. And as I say, if you want to look at the book about the Gardens by the Bay, Oro have got some copies in stock, and apparently I'm going to be signing them afterwards. So there you go. Thank you very much.
Patrick, a bravura performance, as we would expect, and some, I think, very, very wise words and kind of correctives about, I loved your thing about people think they're being virtuous, providing huge amounts of space for bicycles in basements that didn't previously exist. The analysis showing that the embodied carbon in the basements far outstrips any potential gain from people coming in on bicycles. I should also say as a cynical remark that the over-provision of cycling spaces, it's a laughable feature of the London office scene, because actually the spaces provided are never full, and the reason for the over-provision is because it gets you tick box marks on your BREEAM rating. So it looks as though you're being fabulously virtuous, and in fact you're being utterly wasteful. And I guess that theme of we've really got to be, I suppose, more scientific about the way we think about these things. In 2012, the carbon consultant and architect Simon Sturgis gave, as far as I know, the first big public talk at this festival about his methodology for working out the implications of embodied carbon and what that might mean for retrofit programs. Yep. Now, embodied carbon is sort of the biggest game in town. And I wonder if you'd like to elaborate a little bit on whether you think that the drive towards reduction in operational energy is actually obscuring or getting in the way of the embodied energy question, or is it just that the embodied energy is a tougher issue to deal with?
Yeah, I mean, I think it's definitely true to say that as an industry, we are much less proficient at dealing with the embodied carbon just yet. The data has been hard to get. It's starting to get easier. You know, companies are producing environmental product declarations. We've got more information about it that allows us to give a real assessment, a real-time assessment in the design process. I think there hasn't been a consistent way of looking at the two problems side by side. That diagram of the sort of confluence, we're only starting to wrestle with this now. It's not been, you know, we've very much seen this thing as two parallel streams, two parallel problems that we've been trying to fix without necessarily understanding the interrelationships. And I think it's only really as we've sat and started to unpack this in meetings, and I mean, I can't tell you how many hours I spent on the phone with Albert or on Zoom calls during, Albert Taylor of AKT2, by the way. You know, during lockdown, we were doing a whole series of London office projects, and nearly all the calls were only about embodied carbon. We were just, you know, absolutely fixated on trying to figure out how to drive it out. And so we really, and to be fair to Simon Sturgis, you know, he wrote the code at the RICS. We now follow for the RICS. He did the WWF building with us in Woking. So we were doing these calculations back in 2008, 2009, but with almost no data. So, you know, the transformation has been in the UK over 10 years. And I think what's important as a World Architecture Festival to be saying to people working in other parts of the world, you know, we have the information, we have the methodologies. It's not nearly as mysterious as everyone thinks it is. It's actually, it's a bit like QSing, you know. dare I use that word, at an architecture festival. But it's, it's number crunching, it's detail, it's quite exciting as a sort of overall conceptually, but as an activity, it's all about the detail. It's quite tedious to do, but it's super important that we kind of do it.
But as you pointed out, in relation to steel companies, but virtually every industry has got a decarbonisation program.
Yeah.
I'm always struck by those excellent awards that Holcim run. Holcim are a cement manufacturer,
Yes.
and I mean their environmental awards is kind of well, it's not greenwash because there are genuine awards in a very good cause, but they're coming from an industry which is often criticised for the amount of electricity it uses.
Yep.
I wanted to ask you about the question of the relationship between embodied energy, but then the power source that produces it. I mean, if you're making aluminium, but you're using electricity from hydro to power the process, can we take that into account in these calculations about embodied energy? Because they tend to just say some material's good, some material's bad.
Yeah, no, we definitely do. I mean, part of so in the early days of the design process, you use generalized numbers, and then those sort of waterfall chart I was showing you was basically saying, right, if we buy hydro-powered aluminium for the facade, we will save 50 kilograms of carbon a square meter. And then that then becomes a procurement and a cost question rather than a carbon question. And if you've got a client who's interested in driving carbon out, they'll maybe pay the extra for that. The challenge we've got is there's a limited global supply of some of this stuff, and every project in London is lining up to buy the 700 kilograms of aluminium that's being made in Norway this year from hydro or whatever. I meant 700,000 tons. So, but yes, we do look at real products. And so we look at environmental product declarations and we take real numbers as we get into detail. And that's why, Stella Mittal are basically saying they can't sell their steel from Wales because it's all coked and it's made with coal. So it's very, very dirty. But we can buy steel from Europe that's made with electric from wind power and from hydropower, and that has a much lower number.
And probably nuclear power if
And
it's
probably
coming
nuclear
from
power.
France.
Oh yeah, no, almost certainly, yeah. Yeah, nuclear is still a big part of this.
The other, one of the many fascinating observations you made was about the actually this tendency to blame buildings for operational carbon when actually it's mostly the heating and ventilation is mostly other activities. Yeah. And are there any, if you had top tips for the reduction of operational carbon in buildings, in the working of it, are there any that are easily applicable?
Well, I mean, the things that you're starting to see in planning are things like minimizing lifts. We have these lift criteria that require us, they want to have X seconds of waiting time and all the sort of the criteria that drive the sizing and operation of it. Mostly when you go to a lift bank, there's nothing much happening. We moved to double-story lifts, the double car lifts, because they were seen as being, but they're not. It's like driving a London bus up and down a shaft, hugely heavy thing that has to be lifted up and down a shaft, and usually it's got one person in it. So you're trying to find ways of managing traffic, not necessarily using these new technologies. Doesn't always. It's not that they're there for a different reason. They're there to save space, not to save energy. But it's still around the old things around balancing daylight with solar gain. It's still important, but I think much less important than it was. But so the big thing is recognizing that offices aren't occupied 100% of the time in every area. Recognizing that not every office floor has a computer room on it, which we currently design the air conditioning systems in all these buildings to have a computer room on every floor. Everyone uses the cloud these days. Nobody puts big computer rooms on floors, and yet the buildings tend to have capacity built in. So we've got massive redundancy, inefficiency, lots of materials being used for systems that are never being used.
And fairly short time frame to really get to grips with this. Yeah,
2030 is supposedly our window. That's 6 years away. I mean, is it 6 years away? Yeah, 6 years away in a few weeks' time. It's not a long time. We really do need to. That's why embodied upfront carbon is the big game in town, because the operational is a long way off. And I have one. Another area I'm a bit heretical. There's a lot of conversations around deconstruction of buildings and designing for deconstruction, which I think is a very relevant and good conversation to have. But if you actually need to put a lot more carbon into building a building now in order to make it demountable in 60 years' time, I question whether that actually is the right design approach. I mean, we are looking at a couple of projects where we're adding a lot of carbon to make it demountable. We'll figure out a different way of doing it maybe in 60 years, which is not, I say, it's a bit heretical to say this, but I have a bit of an issue with spending a lot of time worrying about, build a building to last 100 years, don't worry about knocking it down. Build for longevity, not for deconstruction. I feel that's the wrong message.
Absolutely. And I can't help but remember a presentation by Autodesk in, I think, 2009, where all their predictions about their programs and their businesses with designers, I think it was a kind of 30-year projection that the vast majority of their business would be related to software programs dealing with retrofit. Mm-hmm. And I suppose, that word is now, completely usable rather than sort of being a trend. I mean, it's absolutely here to stay. Yeah. And I'm assuming that, or let's say, rational retrofit is a big way to address the embodied carbon.
Yeah, it is. And I mean, and adaptive reuse, there's all kinds of, but I think finding ways also you can increase the usability of buildings, you can redesign them within, because buildings were so over-designed in the 80s, 90s, the ability to actually add more floors, again, something we do a lot around London. You can make a lot more out of the real estate without necessarily dropping the whole building. It is becoming a big planning issue in London. I mean, it's becoming very difficult to get permission to knock anything down, as you've probably seen in the media. You've probably written about it.
And to complete a sort of circle, the chair of judges in the retrofit category at WAF this year, I think in Crit Room 5 today, is none other than Ken Yang, the inventor of bioclimatic architecture, when he was doing his thesis in Cambridge, Cambridge, UK, in I think 1967. So
he's a bit of a hero of mine. I should go say hi.
Yeah, it's been a long walk. Patrick Bellew, Atelier 10. Thank you very much indeed.
Thanks, Paul.